Hey, Andre, you there?
Yes, good evening.
So, hello everyone, welcome to our virtual offer holiday for physics. I'm Matt Booth, I am the physics program leader, and I'm joined by Professor Andrzej Zwelendowski, who's the head of school.
I'm head of school, but I also teach on year one as well.
Yeah, so I teach quite a lot in second year. So we're going to share some slides. So Andrej's going to start, he'll hand over to me to talk a bit more about the program details, and then I'll hand back to Andrej to finish off. And then later we'll be joined by Liz, who's a second year physics student, and we'll just have an informal chat with Liz. So at any point, if you have any questions, please put your questions in the YouTube chat. They will come through to me, so I'll be able to see your comments or questions, and we'll try to answer those either as soon as they come in or at the end of our slides. So I'm going to share the slides now, unless you have anything more to say before we start, Andre.
No, let's start.
Okay.
Okay, welcome everyone. So our team tonight, myself, Matt Booth, and Liz will tell you about what we have on offer here in physics in Lincoln. And our city of Lincoln is a truly university city. It's quite compact. It's very ancient city. It was founded basically in Roman times, and settlement existed even before Romans. It's home to one of most glorious cathedrals in the United Kingdom and to one of most modern campuses. Everything is very compact. You can walk in 10-15 minutes to the center of city. You can cross campus in just about as well 15 minutes. This is a really fantastic combination of modern teaching facilities and ancient city with all what students would like, including nightlife and about degrees which we can have, which we have an offer here in Lincoln. That includes full range of physics degrees, bachelor 3 years integrated, master, research degrees, which range from standalone masters and research doctorates, which called PhD, Doctor of Philosophy. We also have various joint degrees. For instance, if you like more math, and then there is joint math and physics. And if you'd like a little bit of extra thinking about foundations of our universe, our sciences, then physics and philosophy is an offer as well. For those who might miss some A levels or have a non-traditional pathway into higher education, we have also Science Foundation year, which can prepare you for year one. Everything what we develop is developed in close collaboration with UK Learning Society for Physics, which is called Institute of Physics. And in Lincoln, we are quite happy about our teaching achievement. Basically, our university holds so-called TEF Gold. TEF Gold stands for Teacher Excellence Framework, and each UK university submits on programs to government for assessment, and you can get gold, silver, or bronze, and we are TEF Gold, so we're quite happy about that. Also, last year, we've been selected by the Times as a Modern University of the Year, which just reflects achievements of University of Lincoln in delivering gold class education. Now we tell a little bit about what is really crucial for physics. Physics is not just something you read from a books, but also it's a subject when discoveries made basically every day. You hear every year about Nobel Prizes. And all our academics here are also active researchers. So we all make our small or large discoveries in varieties of fields. And here, just a bit of glimpse, what science we're actually doing here. And it ranges from fundamental physics, which include fundamental of quantum physics, fundamental of statistical mechanics. It goes into the field of so-called nanostructured materials, or more specifically, soft materials. And that can include like very sophisticated plastics, for instance, with nanostructures. So they can, in the same time, flow if you heat them, and as you cool them down, they form intricate structures, and they can be used in lots of applications, from nanoelectronics and energy materials and so forth. And we work on them both using computational tools, theoretical tools, but also experimentally. We also work on applying various methods into the neighboring fields, like applying knowledge in physics and mathematics and computing, like artificial intelligence, into analyzing blood samples for COVID. When we have been all during pandemic, our academic joined the effort in contributing in basically solving this problem of this enormous pandemic which hit us. Quantum modeling is another part, and then also quantum experimental physics, which includes a very kind of interested object called quantum dots. And you see here a couple of images. One image is from electron microscope, and on the left you see actual sample in a flask which have this fluorescence. And these materials have lots of application from biophysics, medicine, photovoltaics, and so forth. Next part is for those who are interested into objects far away from us. We have very successful astrophysics research based on planetary physics. Exoplanets is a very exciting part, and basically thinking about if there is life somewhere over there, and exoplanets as a candidate, and more recent development in direction of gravity waves as new tool to discover objects far away. And it's not just us who do this research, but students have an opportunity to participate in this, again, small or large discoveries in varieties of ways, as you will see in this presentation. This is just one example when that time, third-year student Michael Birnbaum was doing a project together with Matt Booth, who is here with us, and Fabian Pausson, looking on this very fascinating part on chaos inside of physical systems. And this particular visualization, it's not something out of this planet. It's just so-called double pendulum. And double pendulum, it sounds simple, but as you see from the image, it can create two very distinct pathways. White one is a lower pendulum, and a red one is a upper pendulum. And the lower pendulum behaves totally chaotic, even it just has two pendulums. And a student was involved with that and received, in fact, the prize for this project. And if you go then further, we arrive basically to what we have on offer. So if you choose Lincoln for your study, we have here 16 contact hours per week for physics provision. Everything split here in modules of 15 credits each. And 16 hours comprise of 12 hours lectures, 3 hours physics laboratory. In case if you sit on a joint degree, for instance, math and physics, instead of that laboratory will be additional mathematics. And a special feature is 1 hour tutorial session where you in a smaller groups, 5, 6, 7 students, meet with personal tutor during 1 hour every week, and you discuss various topics without marking, without grading, so there's no pressure in this discussion. And another special features include, for instance, varieties of projects. You see in the list we have here not just projects, which are individual, but also group study and group projects. In Lincoln, we probably have the largest project provision among UK providers, at least the ones I know about. You have already small project work or group study on year 1. It's group because you divide in groups 5, 6, 7, and you choose your roles inside of group, and you produce a professional type report. And Matt will tell a little bit more as he goes into the programs. And assessments is also important part, how you collect your marks here. There is no national kind of standard unified in the United Kingdom. Each university chooses its own way. There are universities where everything, all mark of a module goes in the final exam, and that sometimes creates too much stress. So instead, we design degree in such a way that the exam gives you about 50% of a mark, and in other modules can be 60, and this is maximum. So it means 50 or 40% of a mark you collect in various assignments that you come along the semester. And in first year, you will already know within first 2-3 weeks how you perform, if material is clear for you, because you will get your first assignment. Sometimes they are actually coming on a weekly basis, but they're very short, which can be done in 1 hour. And it helps to arrive till the end of semester. Special features also include here possibility of taking sandwich year after year 2. Or after year 3 if you are an integrated master, and go to industry and spend a year in industry. This is a subject of approval by industrial partner. Some students actually, instead of whole year, choose summer placement. And examples could be in some maybe very unusual places, like in a hospital. But of course, it not work with patients. It working with equipment in the field of medical physics. Another special feature that, as I told, you can participate in research already as a student, and the university provides a system called EUROS, undergraduate research scheme, where you, along academic, do a piece of own research, and examples of images show research in experimental quantum material science of quantum dots, and research in astrophysics as well. And that is example of how successful you can be already as an integrated student. What you see here is actual scientific publication in international journal, where 2 of the 3 authors are our undergraduate students. And that is a very high kind of achievement, where the work is a caliber that it's can be published international journals for all to see and read. So we're very pleased with this type of activities our students can do here. And now I'll pass to Matt Booth to tell a few words about what exactly in our degrees are, what kind of special modules are. Please, Matt.
Okay, thank you, Andre. So I'm going to talk a little bit about the details of the course, but before I kind of get into it, I just want to kind of draw your attention to the kind of structure of the slide. So on the left, we have fundamental and applied physics. So this is where we kind of really do physics. But if you see the middle column in green is labeled mathematical foundation. So it's important that we give you the mathematical skills that you need to be successful in the physics content. And on the right-hand side, you see the kind of pink column labeled student as producer. So this is kind of what Andre was saying about at Lincoln, we kind of try and put emphasis on student projects, whether that's individual projects or group projects. So this is a university-wide ethos, this student as producer. And in other words, it's students being the producers of their own knowledge. So you going out and doing your own research, and whether that's primary or secondary research. So in the first year, let's start on the left, we see the physics modules. They're quite broad in title, so the names are quite long, and they include various different aspects of physics kind of put in together into one module. So geometrical optics, waves and mechanics, and electricity, magnetism, thermal and quantum physics. So the idea of first year is to cover a lot of ground. Some of the things you may have heard of before, you may have even done before to quite a low level. The idea is to cover a wide area of physics and get everybody to the level that we kind of expect from our first year students. You see also here we have laboratory 1, so this is for the physics students and the physics with philosophy students. The mathematics and physics students wouldn't do this laboratory. As I kind of said, you need the mathematical foundations to do the physics. So in first year, we teach you calculus, linear algebra, and probability and statistics. So these are all very useful in the various areas of physics that we'll do. So probability and statistics is very useful for the lab module, for example. But we also teach computing in first year. So right from the very first year, you'll be kind of trained to be highly proficient in technical computing, so various different programming languages. So we start, even from first year, we start with projects. So in the first year, you have a module called Professional Skills and Group Study. So the professional skills part is where you learn how to use various software on computers. Excel, for example, is quite powerful nowadays. You learn some coding in professional skills as well. But the group study part is very much a research project in the sense that you're given some topic in a group where you have to go away and write a report and give a presentation in your group to some academics on the topic. So topics tend to be quite light-hearted, things like physics of superheroes or physics of space travel, this kind of thing. So it's supposed to be kind of a fun way to practice the important skills you need to be an active scientist. So that's the first year. And if we go into the second year, you see the same kind of structure. So this structure will be the same throughout. We have fundamental applied physics modules, such as condensed matter physics, electrodynamics. So maybe these kind of names may be less familiar to you than the previous ones. And you see the names are shorter. So the modules, the physics modules become more specialized as you go through the degree. So like in first year, they were quite broad. In second year, they really start to focus in on specific areas of physics. And these modules will be taught by academics who are specialists in those areas. So Andre mentioned the industrial focus. So this module on the left-hand side, industrial and ecophysics, is where we really kind of highlight this industrial applications of physics. So the way this works is we have guest lecturers come in from various industries in the area to talk about how they use physics in their everyday jobs. So we have people from the hospital come and talk about radiotherapy. We have people from manufacturing industries that use lasers for cutting, and they talk about laser physics, things like that. So this is really useful, not only to learn physics and learn how to apply physics, but to give you some idea of what you could do with your degree once you graduate. And we have some examples of students who've gone on to work with the guest lecturers once they've graduated. So it's a very successful module. And you see here you have laboratory 2, which is just for the physics students. Mathematical foundations, we have differential equations, and again we have scientific computing. So computing is definitely something we focus on. As a physicist, even if you're an experimental physicist, computing skills are really important. And again, we have a group project in the second year. So this is a more experimental project than the project in the first year. So again, it's a group project. It's about developing skills, working in groups, but it's got a more experimental focus. So the kind of thing we've done before. So this picture is an image of one of our students. It's actually Aaron, who you will see later, actually, on a later slide, doing some X-ray diffraction. So that's quite an advanced experimental technique. It uses X-rays to probe the atomic structure of crystalline materials. So very, very powerful and advanced technique. And the task these students were given was to verify that some meteorites, or some supposed meteorites that we purchased from eBay, whether they were actually meteorites or not. Their task was to tell, using this physics technique, whether or not we'd bought some genuine meteorite samples. Another kind of thing the students do in this module is to write a technical manual for an electron microscope. So it's about developing skills that are useful, will be useful down the line. Okay, so on to third year. So we'll start again on the left-hand side. We see some physics modules. We have quantum mechanics, statistical mechanics, physics of the universe. This is kind of cosmology and some gravitation and some kind of astrophysics. And this module underneath physics of the universe called advanced topics. This is similar to the industrial module in second year, except instead of inviting local industrialists in, we invite collaborators from different universities, so our research collaborators, to come and talk about their research in physics. So again, it's based on guest lecturers, but it's more on a research focus. Now you see some modules, some names are written in red. These are the modules you get to choose from. So you choose one of these 3 modules. We have methods of mathematical physics, which is a very theoretical module. So if you're interested in theoretical physics, maybe this one's for you. We have fluid dynamics, which is also quite a theoretical module, but it's more focused on fluid dynamics, as the name suggests. But this could be useful in industry, for example. If you go into industry, you want to know how fluids flow in pipes, this kind of thing. It's a very useful module. And finally, we have physics pedagogy. Now, this module is where you actually can gain some experience doing some teaching in an actual secondary school in Lincoln. So it's a very, very popular module. And if you're thinking about possibly going into teaching as a career, it's a great opportunity to get some experience and something fantastic to put on your CV. And again, we have great stories of students who've performed so well at the schools they visited that the school has hired them immediately upon graduation. So we have really good links with the schools in the local area. In terms of mathematics in third year, so you see the focus starts to move more on physics than the mathematics as we go through. So there's only one mathematical module in third year, and that's numerical methods. So this is very much computing, how to calculate things that you couldn't do on pen and paper using a computer. And finally, the kind of culmination of the degree, as far as the student as producer ethos goes, is your individual project in third year. So this is the thing closest to what people would call a dissertation. Okay, so it's your main kind of big chunk of work in your last year. And so I'll talk about that on the next slide. So here are some examples of the individual projects that you can do. So this is just a glimpse of the possible projects. So the way it works is you're given a list of projects to choose from, and you would have a supervisor for the whole year. So one academic lecturer will be your designated supervisor for your project. You would meet with them once a week to kind of talk about your progress. It is very much an independent, individual project, but you are supported throughout. So just to kind of read off some of the projects we've done in the past. The first one there is the chaotic double pendulum. So that's related to the image you saw earlier. You can do some work with the characterization of quantum dots, which are those tiny crystals that Andre showed earlier. You can do some mathematical modeling. So there's nice projects my colleague Manuela came up with to use mathematics to model the living dead, so zombies. But the same mathematics is used to model pandemics, but it's a bit more light-hearted. You can look at things like radars, atomic force microscopy. You can try and incorporate some machine learning, which is a very kind of popular thing nowadays, into your physics projects. So it's a very powerful computational tool you can use in your physics work. You can do some astrophysics. You can do some really deep theoretical stuff to do with electromagnetism, for example. And this next project that looks at the effects of gravity on radiotherapy was actually done in collaboration with our colleagues at the hospital. So the physics team at the hospital in Lincoln helped us come up with this project. So I said you'd be given a list to choose from. This project was actually kind of developed by the student themselves. So if there's something you really want to do that's not on the list, it is possible to actually propose your own project. You just need to kind of let us know in advance, and we will try and kind of negotiate with you to make sure the project's suitable, achievable. So we really try and give you what you want here. So your project is where you can really specialize and start to move towards your career goals. And it's something fantastic to talk about in your CV, for example, or interviews. Right, so so that's the BSc. There is the option to transfer onto an MPhys, or you can start directly on the MPhys. Now, what's nice about this at Lincoln is you don't have to decide until the end of your third year. So you can go all the way through 3 years on the BSc program, and at the last minute you can switch to MPhys and do an extra year that would be an integrated master's. This is not usually possible. This is something we've designed intentionally into our program. So the MPhys and the BSc are parallel to allow students to switch between them right until the last minute. And students have really done this literally at the last minute, and it's all fine. So the fourth year, it kind of focuses on our research specializations in the school, which, as you kind of maybe saw earlier, is nanophysics and molecular modeling. So this involves quantum mechanics, statistical mechanics. And so these two modules are done by everyone, but again, the modules in red are choices. So you can choose between advanced instrumentation, which is like an advanced lab, so you learn about various advanced experimental techniques. Or you can choose theoretical physics lab. So that's with Andre, the head of school, and it's a very theoretical module. So maybe if he wants to, you can say more about that later. And in the mathematical foundations, you may be kind of surprised to see this module called financial kinetics. So there's a couple of reasons why we include this module in a physics degree when you may not expect to see it in a physics degree. So the first reason is that, as Andre maybe we'll kind of mention towards the end of the slides, a big employer of physicists is the finance sector. So a lot of physicists go into finance, into banking, other financial institutions. And because of the problem skills that they have and the mathematical foundation that they have, they're very kind of highly valued in this sector. So that's one reason we decided to put this in there, is to give you an edge in this kind of job market, if you wanted to do that. But the main reason we put this in is that the mathematics used to describe financial markets, exchange rates, things that are kind of unpredictable and have some kind of chaotic nature to them. It's the same mathematics that's used to describe a lot of things in physics, so-called kind of stochastic dynamics. For example, Brownian motion. You may have heard this term before, where you have kind of like the air molecules, kind of the motion they undergo, where they're kind of bouncing off each other. This is very, very kind of unpredictable motion. When you kind of follow one particle, it's very hard to predict what it's going to do. And for this same reason, the mathematics used there are used in financial markets. Yeah. So again, we have this student as producer kind of ethos, kind of shows itself in the fourth year as well, where you do a really big project. So this is the whole of the second semester is a project. So all of these modules in the left two columns are done in the first semester, and you have the whole second semester, which is about 3 months, to really focus on a project. So the project would be more advanced, so the project would be research level, and the fact that it's kind of the only thing you're doing allows you to really immerse yourself in the project. So the project you do in third year is alongside lectures. So it's very difficult to really immerse yourself in the project when you've got all these modules going on at the same time. In the fourth year, it really should feel like you're a research student. Okay, so it's like a mini taste of what it would be like to do a PhD, for example. So again, you would be given a supervisor, and you meet with your supervisor every week to discuss the project. Even though it's a very independent, individual thing, you would be supported throughout. So I'm going to speak very briefly about the options that you can do in terms of mixing physics with other subjects. So, for example, you can do physics with philosophy, which is a relatively new course here. So, for example, in the first year, you would still do lab, but you would be doing other modules such as introduction to philosophical logic. So logic is extremely important in physics. So this is very, very kind of very, very good thing to do. Introduction to moral philosophy, philosophy of science, which is obviously relevant to physics, and existentialism and phenomenology, which is kind of important if you're interested in the kind of philosophy of quantum mechanics, maybe. This could be very, very relevant. In third year, the only difference is you do this big module, contemporary problems in philosophy. So this is a bit like the advanced topics in physics module, except it's kind of more advanced topics in philosophy. So physics with philosophy is available. Feel free to get in touch with us if you have more questions about this joint program. So you can also do mathematics and physics. So the physics with philosophy, because it's physics with philosophy, it's 25% philosophy, 75% physics. The mathematics and physics, the and tells you that it's 50-50. So this is 50% mathematics, 50% physics. So in the first year, very, very much similar, except instead of lab, you do extra algebra. And again, in level 2, instead of lab, you do extra algebra. So algebra is very much a focus of our mathematics research stuff here. So that's where the extra maths comes in. In third year, it's very much the same, except you have more options. So you get an extra mathematics option, tensor analysis. So tensor is very useful in general relativity, for example. So that's the mathematics and physics course. So again, these are I've done a very quick overview of the courses there, the options you have. But please feel free to get in touch if you have any questions. I'll put my email address in the chat in a moment. So I'll pass back to Andre. So
yes,
thank you.
Thank you, Matt. I'll just very briefly say that it's not only about learning in labs and this. There are also more things we do in a school. We very compact school. It's kind of impossible here to get lost in the crowd, so to say. And we have a strong sense of community. Images here depict our annual end-of-year physics parties, which we organize in a house called Doddington Hall, which once was a house of famous scientists who, together with very famous Benjamin Franklin, who's mostly remembered, of course, in the United States, together and a few others, they developed lightning rod protections for buildings. And every year we go to with students there and celebrate their achievements when students receive certificates for their annual work. And also the students can mark academics whose teaching they like during the year. And this is basically this event of certificates. And then it's not just about parties. We have more. We have another sort of parties where students come and they have mathematical or physical games activities. And as you see, so they quite enjoy this type of activities. And not only that, we also organize various trips. This particular trip happened to be to observe one of actually Europe's largest telescopes. And students could experience, that was particular in La Palma, experience what does it mean to be at that facilities, how astrophysics is done in modern days.
So can I just say,
yes.
This is completely paid for by the school. So all students in the third year on physics in this, it's the physics of the universe module, go on this trip for free, paid for by the school. Unfortunately, though, this year, as you may have seen in the news, there was a volcano in La Palma, so you couldn't go this year, unfortunately.
Telescope been closed this year, unfortunately, due to lots of dust from the volcano.
So you can't
But
see much.
yep. And other bits of activities we have, as I mentioned, physics is a lot about research and discoveries, and that also means scientists go to various so-called conferences. They exchange ideas, and our students can participate in that. So this is one of our first student cohorts. They participated in how lasers are involved in various industries. There are also conferences specifically dedicated to undergraduate research. I mentioned, and Matt mentioned, that we have lots of projects, and we have project during degree, but also we have summer opportunities for students, and then they do their piece of research. They can present it in a British-wide conference for undergraduate research, and our student, as you see, participated in work on so-called granular materials. And granular materials is very mysterious and somewhat objects. There are simple examples like sand, but there are other examples, and they still not resolved. Even it looks like sand is very simple, but the mysteries are still there. And if we go further, there are also conferences which enlarge participation of underrepresented groups in physics. For instance, undergraduate conference for undergraduate women in physics. And our students participated in that one. Even during pandemic time, the conference was online, but the students had this chance. And as we go out of pandemic, more and more these activities go back to face-to-face. Right now, all our teaching, for instance, done face-to-face. And now we mentioned that we not just teach in class, but we also provide lots of various video materials of public lectures on varieties of topic. They all presented on YouTube. You can watch and have a bit of flavor, what academics we are, what topics we research. This particular set of lectures been on British Science Week. Then we have varieties of lectures in the field of topics in physics, like do you understand maybe first and second Newton law really deep, or we have astro charts, or we have dedicated channel with lots of small videos, sometimes as short as 30 seconds, about lots of topics in astrophysics. So you can come along in these channels and just kind of have a taste of our way of doing physics here in Lincoln. And I just very briefly mentioned that jobs in physics, and we have already graduates in our school in all degrees. And in simple words, physicists can find jobs almost everywhere, including NHS, as you see in this list. And of course, I already mentioned NHS, it doesn't mean work, with patients directly, it's working with very complex machinery. And finances, you see on the top, it's also because physicists know how to solve problems which nobody solved before them, because physics is about solving what wasn't solved before. That means it's quite challenging problems, and they are sought in all kind of fields and in finances in particular. And we just mentioned a few examples of our graduates. Flick, who was our BSc Physics graduate, she works as a in cybersecurity engineer in airspace in a part of BA in Britain. And you see what kind of responsibility she has is designing electronics, working with various algorithms. She directly uses varieties of knowledge and modules she studied, and you also can see what starting salary in that particular field of employment is. And then we mentioned Aaron, who appeared before in Matt's talk on the image with group project. Aaron got into the school, and he immediately got like one would call dream job for a school teacher in he became physics teacher in the same very school when Isaac Newton was pupil himself. And obviously he uses all his physics knowledge there to full extent. And Hannah, BC physics graduate from 2018. She actually spent time in summer placement in hospital and decided that medical physics is something she really likes. So she went to further training in that field to become a medical physicist and basically help doctors to save lives and to eliminate diseases using complex physics equipment. And with that, we arrive to the end. So there is time for questions, but also time to chat with our current student, Liz, who is waiting for us to join us in this virtual room.
Yeah, so what I'm going to do is I'm going to keep my eye on the YouTube chat in case there's any questions comes in. But what I'm going to do now is add Liz. So hello, Liz. I think you're on mute. You're going to take your microphone. I'll remove the slides.
Sorry.
So we can see that. There we go. So we're a bit bigger. So yes, this is Liz. She's a second-year physics student. So hi, Liz.
Hello.
I thought we've got maybe 15 minutes or so to have a quick chat. I'll ask you some questions, then you can maybe ask us some questions or however it goes. So the first thing I wanted to really ask you was, and I think I can imagine the answer to this question is, if you think back to when you were kind of looking at universities, thinking about what to do at university, do you remember how you decided to do physics? Did you always want to do physics? Or?
Well, I really enjoyed science growing up, so I'd like to take trips to the library and stuff. And the main problem was the science section in the library consisted of 6 books, and one of them was quantum physics for dummies, I think it was. Okay. And I just read that, and I was like, that is really cool. And I had a couple. Obviously, I had lots of questions because I was a GCSE student, and I was told that electrons were particles, and kind of like to adhere to the Bohr model of the atom. And then now I'm being told that there's a whole other model that's actually a bit more correct. And I was very, very confused. So I asked a couple questions, and then that generated more questions, and then ended up doing a degree in it, basically, if that makes sense.
Yeah. Well, we're glad you did. So I kind of guessed that physics was always going to, I mean, I remember you telling me you've been reading physics since you were quite young. So I guess physics was not a big choice to make for you. But when you were looking where to go, what was it about Lincoln that made you think, I'll go there?
I went on like a maths and physics course thing, like in my first year of A-level here, and it was really good. Yeah, there was like a couple of like mini lectures. So someone did one on Pascal's triangle, and then someone did one on like chaos theory. And then we ended up approximating pi with a pendulum, which was really fun. So I thought, yeah, I'll go here. It's cool.
Nice.
And I ended up going here. So yeah.
So now you're here. What is it that you like most about Lincoln? Is the city or the university in general?
University was the opportunities that you have to not only expand upon your knowledge, but to gain experience in loads of different areas, not just research. Does that make sense?
Yeah.
Yeah.
So you like living here then? There's the city here.
Yeah, it's all right. It's good.
So I think that, I mean, for some of the staff who, I mean, I actually am from Lincoln, so I know Lincoln very well. But I think some of the staff, I mean, Andre probably didn't know where Lincoln. You probably never heard of Lincoln before coming here, right?
No, actually, it's true. I did. I did not. In fact, it's not quite true. I kind of did not hear about Lincoln as a city, but I knew about Lincoln Cathedral from drawings of John Ruskin, but I did not quite connect these two pieces together. That those drawings and this city is the same kind of thing.
Okay, but I think for a lot of the staff, they really enjoy living in this city. It's not a big city, but it's got lots going on, and it's a very beautiful city. So anyway, so what is it about physics at Lincoln that you like? Do you like studying physics at Lincoln? Do you like the school environment?
Yeah, it's really nice. Yeah, I love studying physics at Lincoln. It's great. There's lots of like extracurricular stuff as well. So Matt and Fabienne do a nice little general relativity club, which is really good. And we've paused the philosophy one for a little bit, but we do that. We look at the book called The Structure of Scientific Revolutions, which is basically about the philosophy of science and the history of science as well. It's nice.
So that's actually like, you may have heard of the word paradigm, the phrase paradigm shift. This is the book that kind of came up with that terminology. So yeah, Liz mentioned the general relativity group. We call it the gravitation congregation. So we spend about an hour every week working through a general relativity textbook. So it's very advanced stuff. And there's no assessments or anything. It's just a very informal chance for staff and students to do some advanced physics together. So we actually did it today.
Yeah.
And I was feeling quite tired, so Liz did most of it today. So what's your favourite module?
Oh, so far, favourite module.
So far, yeah.
That's so difficult.
Sorry.
It's probably between electro and Lagrangian.
So electrodynamics.
Yeah, between those two, probably. Because they both kind of complement each other, so it's difficult to choose one between.
A bit of overlap,
Yeah.
So maybe we can ask you, what are your ambitions? So what are you hoping to do with your physics degree?
Oh, I haven't really thought about that. I guess I would really like to go into research, maybe get a PhD if I can in something cool, and then just kind of write papers for people and put stuff in journals. That's the dream. I don't know if that'll work. We'll see.
I don't see why not.
Yeah.
So any idea what area? I think quantum stuff I think you like, right?
Yeah, quantum, StatMech's fun. Solid state's all right, but I don't know a lot about solid states. We need to look into that a bit more. But yeah.
Well, you're doing that at the moment, right? That module.
Yeah.
Right. Okay. So, do you have any questions, Andre?
And what do you think about the seat? And do you know that graduation in just a short time will be in this cathedral on the top of the hill?
I've not been in the cathedral yet. I need to go and take a visit because I had the moon in there a couple of weeks ago. Yeah, it looks really beautiful.
Still there.
Might be still there. Don't know.
Sure. But yeah, so you, even if you don't go into your graduation, when you graduate, you will go to the cathedral because that's where the ceremony is held.
The graduation ceremony in cathedral with a party afterwards in a castle, and it's not just cathedral house of like a religious house, but interesting enough, one of bishops of Lincoln of 13th century, long ago, Robert Grotest, is now actually, there is lots of modern research done discovering his writing, and there is strong opinion that he was the first British so-called physicist. Okay, but physics did not exist in 13th century. But what he wrote about light and about basic expansion of universe, of course, he even did not have those words, but people kind of now rediscover his writing and trying to understand them, and even put some equations there. And there is strong claim that he was the first physicist in British Isles, and that happened to be here in this cathedral. So just kind of physics from Middle Ages to modern days.
Very good. So I guess we can kind of wrap it up there. Maybe one last question, Liz. And I don't know if this is a bit tough, but for people watching who are thinking about going to university, maybe to do physics, looking about where to go, do you have any advice for anybody watching in that situation?
That's tough.
Sorry.
Definitely have a look at what different unis have to offer. So, like for example, our course, as Matt said, is very kind of project-y orientated. So a lot of opportunities to get into research and things. And other unis, their focus is different. So maybe have a look at where you kind of what areas you like and what areas you'd like to go into, and where research areas are in different universities, and just kind of look at what they have to offer, because it's different where you go, you know.
Yeah. So the best thing is to speak to people there if you can. Okay, so let's finish there. So thank you very much, Liz, for joining us for that. That's very, very interesting. Thank you, Andre, for helping me talk about the program. And thank you, everyone, for watching, for your attention, and enjoy the rest of your evening. And Liz, I'll see you tomorrow in lab, okay?
Cool.
Bye.
Okay, thank you,
Bye.
everyone. Bye. Bye.